So let's remind ourselves of a couple things that we've seen early in the semester when we were talking about electricity. Notably, what happens when you put a charge in an electric potential? Well, then the charge has potential energy. Just like if you put a mass into a gravitational field, that mass has gravitational potential energy. If you put a charge into an electrical field, the charge has electric potential energy. Although we don't typically talk about it in terms of the field in electricity, we talk about it in terms of the voltage or the potential. So let's remind ourselves, if I have two plates that are charged up and to 1 volt of potential difference across them, and I'm going to take a proton, right? A proton has the fundamental charge in positive form, an electron has the fundamental charge in negative form. Here's the fundamental charge. There's been some rounding, right? It's got more decimal places, but 1.602 times 10 to the negative 19th coulombs. I make this a positive one, that's why I put the positive here next to the E. The E is the symbol for the fundamental charge. And put this in this potential. And ask ourselves, how much energy does it have? Well, if I remember that the potential energy is equal to a charge times a voltage, then I can substitute in this charge, E, 1.602 times 10 to the negative 19th coulombs, times 1 volt, and I get this, 1.602 times 10 to the negative 19th joules. Okay, so this is energy now. It's a very small amount of energy. As it turns out, though, when we're dealing with the very small world, like electrons and protons, really small amounts of energy are what we have. And it becomes really tiresome to write 1.602 times 10 to the negative 19th joules over and over and over and over and over again. So what we normally do when we do stuff like, when we come up against this situation, is we redefine our unit of energy to make it easier to write. I mean, you do this all the time when you say you drove 10 miles. Like, but you could say, oh, I drove 50,280 feet, and people would look at you like you're kind of, or I guess it'd be 52,800 feet, and people would look at you like you were crazy. We wrap up that many feet inside a mile, and it makes it easier to handle. Well, we're going to wrap up this little bitty amount of energy into a new unit called an electron volt, or EV for short. That makes it easier to handle. So we're going to define this amount of energy, 1.602 times 10 to the negative 19th joules, as 1 electron volt, or we usually say EV. So the unit here is EV. Notice this is not a unit, this is an equation. This is a term, a charge times the voltage. But doing that sort of invites the usage of this unit. So an EV is a unit of energy. Of course, if I do that, I can redefine lots of other things that I've had. So we saw Planck's constant in the last video, and it was, I gave you the value of that in joule seconds. There's going to be another value of Planck's constant for EV seconds, and those are just constants. You can look them up. Just be aware when you're looking up things like Planck's constant or some other constants, whether or not what number you use depends on the units. So sometimes you'll need EV seconds, sometimes you'll need joule seconds. It just depends upon what you're asked. Just make sure you know what you're doing. Okay, now with this said, we can also work backwards from this. If I were to say, okay, well, since this is a charge times a voltage, and I can say, well, okay, if a particle has 1 EV, and I know that the charge of that particle is this, then how much voltage did I accelerate it across to get 1 EV? And I could just go backwards and say 1 volt. So maybe if you don't see that, let me say, if you have, let's say, 10 electrons, sorry, 1 electron with energy of 10 EV, through how many volts did that electron get accelerated in order to have 10 EV? And because I'm dealing with an electron, which has the fundamental charge, this is a really easy problem to solve. Just it's just 10 volts, right? If I have 10 here instead of 1, then I plug in a 10 here, and I get this times 10 EV. And so if I know the EV, if I know the energy in EV of my electron, it's really easy for me to say, oh, it's just 10 volts. In this case, 10 volts that it got accelerated across. All right, that's the background to the next thing I'm going to talk about with the photoelectric effect. And so here you have the a general apparatus for the photoelectric effect. So we're going to let light be incident upon this plate, and then we're going to find a current flowing around. And I have here what's called a variable voltage. Usually the symbol for this looks like this. This is basically a voltage source that I can change. You know, a battery is a voltage source that you can't change. But if you've ever used a power supply in a lab or something like that, you have voltage sources that you can turn a knob and go from 0 volts to however many volts they're rated for. So let's say I have this situation. I have light coming in here, and I have this variable voltage, and I initially have it set to 0. And of course I also have an ammeter here, so I can measure the current. And so I have current flowing, my ammeter measures it, and then I start to turn up my voltage. And I do it slowly so that I can see. And at some point, the current stops. What does that mean? Well, I have wired up this voltage. Notice, if the current is flowing in this direction, I put the positive terminal to oppose that. So as I turn this voltage up, I start to try to drive a current opposite this one. Of course, to do that, what I have to overcome is the energy of the electrons as they're moving down the wire. So what I can say is that whatever voltage I find that stops the current, that is, I can then tell the energy of these electrons by reading the voltage. For instance, current stops at 15 volts. This means the kinetic energy of my electrons is equal to 15 EV. It's really just that simple. If I find that the stopping potential, that's what this is called, the stopping potential, that's the potential that stops the current, is 15 volts. That means the kinetic energy of these electrons is 15 EV. Now, what can I do farther than that? Okay, fair enough. What if you know the frequency of the light, and you're asked to find the binding energy of the metal? Remember what that is. These photons come in with some frequency HF. That has to be great. The energy HF, I said frequency HF, they come in with some frequency F. That means they have an energy HF, where H is Planck's constant. So if they come in here with HF, they have to have, that energy has to be greater than the binding energy of these electrons in order to knock them out of the plate in the first place. Okay, so what that means is that the total energy of the photon has to appear in the electron as whatever this is, right? This 15 EV, this is the energy that they have, plus the binding energy of these of the electrons when they're in their atoms. So see what's happening? The whole energy of the photon has to overcome the binding energy, and then whatever is left over appears as the kinetic energy of the electron. Some of this initial energy is absorbed getting the thing out of the atom, and then whatever is left over appears as kinetic energy of the electron. So if I'm given F in this situation, I can just formulate HF. I would need to do it in electron volts, right? Because I have this in electron volts, and so I would look up the Planck's constant that's given in EV seconds instead of joule seconds, multiply it by the frequency, and then subtract the binding, subtract this kinetic energy, and that would give me the binding energy. This formula is written in get the notation that your book uses. It's written like this. Kinetic energy is equal to HF minus the binding energy. I used kinetic for here and rearranged this expression. I will say your book is the only one that I've ever seen to use this particular notation. You will very often see this written as kinetic energy is equal to HF minus the Greek phi. We usually call that the work function. It means the same thing as the binding energy of the electron. So we know how to get the stopping potential. If I have an electron that it has 15 eV of energy and you say what's the stopping potential, it's just 15 volts. If you're told that the stopping potential is 15 volts, and what is the energy of the electron? Well, it's 15 eV. Once you have that, if you know the frequency, you can always find the binding energy. Of course, if you know the binding energy, you can then find the frequency. In general, this is a pretty simple formula to manipulate as long as you know the appropriate quantities.